Thank you very much. My name's Lucy. I'm an engineer working at Uber, and I'm a contributor to Kubernetes. And I'm honored to be joined on stage today by Sandeep.
Hi, everyone. I'm Sandeep. And I work as a lead software engineer at Zen. I'm a co-chair of the CNCF, Dev, and the Hard of Sharing Working Group. And I'm also part of 6 country backs. And it has been a wonderful journey for me trying to learn Kubernetes. So we are here to demystify how we learn Kubernetes the hard way from the wonderful blog that Kesley has written. Thank you.
Awesome. So today, we are going to be building a Kubernetes cluster without scripts and without tools. The first thing I have to say before anyone gets too inspired, don't you dare do this in production. If you do, it's on you. This is a single node cluster. If that one node goes away, you are dead. This is also live, and we actually mean live. The machines are in Amsterdam over the Wi-Fi. There is potential that this goes wrong, and we'll improvise if it does. But just be prepared. This is not a well-prepared and perfect thing. We're also not starting with absolutely nothing. There are configuration files that exist on the server, but nothing is turned on right now, and there is nothing to connect to right now beyond just an SSH terminal on a box. And because if we were, we'd be here for like 5 hours. Outside of that, we're also not going to go into the infinite minutiae of Kubernetes. You know, we will make comments about CRIs and CNIs if you know about those, and about authentication. But this will more be a passing glimpse over the internals. The idea being that if you have been using Kubernetes but not having to operate clusters yourself, this might be quite interesting to you. We also, as a complete side surprise, have Kelsey Hightower here, the man who, much to my annoyance, created Kubernetes the hard way, which I now have to do live on stage. But I think he said that he can give a brief presentation on why this approach to building a Kubernetes cluster even exists. So take it away, Kelsey.
This is so random because I was walking from lunch, and I saw one of the organizers like, hey, we're doing Kubernetes University or a Cloud Native University. And I was like, what's the next talk? He's like, Kubernetes the hard way. I was like, the hard way? Like the thing that I put on GitHub? He's like, yeah, but they're going to run through it live. I was like, all right, I'm going to go check it out. And I figured we would owe you a reason why this thing exists. When Kubernetes first came out, I was an early contributor working at CoreOS. And at that time, everyone was saying Kubernetes is way too complicated. It's impossible, it's too complex. And the truth is the complexity has to live somewhere. And the earlier attempts were to create these little shell scripts. The most famous shell script is called, I think it's like kube-up or kube-sh. And that thing, if you ran it, it would run for like 700 years. And then a cluster would appear. And then when it broke, you had no idea how to fix it because you have no idea how it works. So we went back and forth, and I decided that 2 things happened. When I joined Google, we decided to get all the engineers who work on Kubernetes in a room to figure out how they can make it easier or better to work with. 2 things came out of that. kubeadmin, some of you have heard of that tool. Ideally, it's a progressive way of installing Kubernetes. We did OS packages, but I also believe that there's something missing. It's not hard because it's not easy to install. It's hard because no one understands it. These are very knowledgeable system administrators who are managing these systems for a living. So I decided to create Kubernetes the hard way. No scripts, no automation tools. And my goal was to show you step by step every logical thing you had to do to create a Kubernetes cluster the hard way. And I think for a lot of people, that was the #1 teaching tool to help you feel like you understood the thing you were being asked to manage. So I hope today you get to see this thing get assembled in real time. And thanks for doing this and keeping this project alive. Thank you all.
Thank you. Thank you.
Awesome. So with that, I think, Sandeep, you're going to talk about what we're going to be doing today.
So here is our plan. We'll start with the API server, which is sort of like the Kubernetes front door. And then we are going to add etcd.
Yeah, go ahead.
etcd is storage. And then usually we bring in the controller manager and the scheduler to manage our work, and then kubelet and kube-proxy to run it. So by the end, you will see a pod live. So I'm going to kick off with the API server. So the API server is the sort of Kubernetes core. It is the heart of the Kubernetes control plane. Think of it like the front door of your Kubernetes cluster. And for a single interaction with Kubernetes, whether it is to the kubectl tool, your own custom applications, or your cluster management tools, it all goes to the API server. And it does not store anything. And it is also the only component that talks to the etcd service, which is the distributed key value store that holds all of Kubernetes data. So the API server is stateless. What does it mean is that it doesn't store any data in memory. It pulls fresh data from etcd every single time. So the advantage is that you can actually run multiple API servers. You can spin 3 or 5 instances and run them behind the load balancer, giving you a lot of high availability. The API server also exposes API to both the HTTP and the gRPC. And that is how clients interact with it. For example, the kubectl uses HTTP, and other internal components use gRPC for efficient communication. So what this does is it validates all the incoming requests. It validates all the incoming requests, ensuring that they conform to the Kubernetes API schema. This is really critical for maintaining the integrity of the cluster. So when you run a command like the kubectl create deployment, the API server receives the request, validates it, and then stores the desired state in etcd. And later, the controllers will act on the state to bring the cluster to the desired state. Now, let's talk about etcd. So Kubernetes needs a database that is not just reliable, but globally serializable. So globally serializable means that any change made to the database is immediately visible to all the components in the cluster. There is no delay and no old data. This is very essential to avoid situations where different components make conflicting decisions based on outdated information. Like, imagine that you are withdrawing a cash from your account based on yesterday's balance. You don't want that to happen. So originally, etcd was a part of container Linux, but now it's a standalone project widely used in cloud-native environments. It is a massive key value store where Kubernetes stores all its configuration and state data. So you can think of it like a giant filing cabinet. And the key benefit is the global consistency. And it is also the Achilles heel, because of its global consistency, there is a limit to how much you can scale. For thousands, it works very fine, but think of millions, and the Kubernetes starts hitting its limits. Okay, so I think now we are going to have like a short demo, and in the demo, we'll be starting first the etcd service, because that is where Kubernetes stores its data. So we'll first start the etcd service, and then we'll start the API server, and then you will be able to see how the cluster starts and how the cluster information happens.
So you just hit here, and you are on here. Cool. Go for it.
Okay, so here.
Oh, you want to make that a bit bigger, maybe?
I'm going to make it a little bigger. Okay, so this jump box is a sort of a machine. It is just a machine where we have admin access. So it is a box that we are using to configure the server and the node. So here I'm just SSH to the jump box. Okay, and now, okay, so this is the alias that I've created to connect to the server. So when I create to the server here, okay, I'm logged into the server node here, and here if I do, oh, 1 second. I think the keyboard is changed, so I'm struggling.
No worries.
Yeah.
This is my localization on my keyboard.
Okay, so you can see it is not running. So I'm just going to start the service now.
Yes, absolutely. Anti-theft device.
Okay, now how do we know if the service is started or not? So just let me quickly show you the alias for this. Okay, and now if we are going to see the status, if the service has started or not. Okay, so you can see here that it is active running and it is ready to serve the client's request. Okay, so the next step is now that the etc is up, we are going to start the API server. Okay, so we have started the etc service and we have also started the API server. Okay, so now we are just going to do like a quick check here. So I'm going to come out. I'm going to come out of the server node and I'm going to go back to the jump host. Okay, and then in the jump host. Okay, I think we have to wait for a while before the cluster comes up.
No, it's up. It's running. Yeah, it's running.
I think you could continue in the interest.
Yeah, absolutely. Yeah, okay, cool. So we have a running, what is it? We have a running etcd and we have a running cluster. If I go on here and I ask for resources, there's nothing there yet, but we have something we can talk to. Awesome. Now, given that though, let's see if we can start up an application already. So let's try and create a deployment running Nginx, very famous web server, using that image. And so, cool, deployment gets created. But if I go and have a look at the deployment, I'll see that there doesn't seem to be anything there. And if I look at the deployment object, nothing seems to be ready. So what's going on here? Well, if we come back here, I will explain. So what's going on here? Well, the API server and etcd, sure, they can store the desired state that you want for your cluster, but they can't actually do anything on their own. It's just an API and a data store. So how do we actually make this do things and affect change? Well, we use controllers. Controllers can be from the community. There's a really cool controller called Cloud Native PG. If anyone from that team is in the room, I really like it, thank you. You can also write your own controllers. Within Uber, we have controllers to manage network groups and services, but there's also controllers that are shipped with Kubernetes. Importantly for us, given we're creating a deployment, that includes the deployment controller. So what the heck does the deployment controller do? It interacts with a few other objects, but in effect, it creates pod objects. Pods are effectively a unit of computation in Kubernetes. It can have multiple containers and etc. But we need to get to that point before we can do anything. So given that, let's create a kube controller manager so that we can try and get some pods on this machine. So I'm going to SSH onto the server. And from here, I'm going to have a look at a lovely file I prepared earlier, but it's not running, so not cheating. Manager.service, which is here. So what the heck is this doing? So this has a kubeconfig file so that it knows where the cluster is, how to authenticate to it, and it has some other options which, in the interest of time, I'm not going to get too much into. Importantly, though, if I turn this on like this, and then I check the status of the systemd service, we see that it comes up and is active running. So now what? So if we come back now and have maybe a look at our deployment now, it's not ready still, but if I have a look at, and sometimes I'm impatient here, so you're going to have to give it a second. I am impatient. It takes like a few seconds. We found in the drive. There we are. See? I definitely wasn't sweating buckets then. So cool. So a pod suddenly appears, but it's not doing anything. It's just kind of sat there in this pending state. So what's going on? Well, it's all well and good to create a pod and say, I want you to run this container, but that's not very. But now you need to decide where to actually place that. Kubernetes can't just magically cause your containers to get free compute, although I wish it could. That'd be awesome. you have to find a computer to run your workload on, and to do that, you use a kubescheduler. Kubescheduler basically looks at the available computers in your cluster. I'm keeping simple here. And it chooses the most preferable one at the current time, and it says, OK, this workload can run on this machine. It looks at constraints. Maybe you might set constraints like, please do not run this workload on nodes, on these sorts of nodes, maybe like given a CPU arch or something. Or please prefer to run these workloads first. And there's a lot more customization in there, but in the interest of time, I'm not going to get into the infinite minutiae of it. Importantly, so let's try and start kubescheduler and see if that makes things any better. So I'm going to SSH back onto the server and have a look at the kubescheduler systemd service. And in here, even more simple this time, it is literally just a kubeconfig. It's literally just a config file. And if we have a look at this config file from memory, then it's effectively just a kubeconfig that says, where is the Kubernetes cluster, or effectively the API server for the Kubernetes cluster, how the heck do I authenticate to it? That's all it has in there. So given that, let's start up kubescheduler and have a look to make sure it came up properly. Cool, so we have kubescheduler. So surely my workload's running, right? Well, if we have a look at the pod, oh, it's still pending. Well, let's maybe go in and have a look at the description on it. And it says, and now suddenly it says failed scheduling. No nodes available to schedule pods. Well, why is that? Because we haven't actually created any machines where we can run workloads yet. So now we need to create one of those. And what runs on those? The kubelet. The kubelet is a binary responsible for looking at, for a given node, what workload should be running on it, and causing those workloads to run. It interacts with something called the Container Runtime Interface, CRI. We don't need to go too much into details of that, but many systems implement the CRI API. Docker does, Containerd does, Cryo does, many more available. The kubelet runs on every computer where you want to run workloads. In general, it should not run on the machine that actually serves your cluster control plane. Why? Because if you put a noisy neighbor workload on that machine, you're not just going to blow up the node, you're going to blow up your whole cluster and be in a very bad position for recovery. So given that, let's maybe have a look at putting a kubelet on here. And we are actually following that practice of not co-locating on the server. We have a second machine where we are going to run the kubelet, because we're really advanced here. No. So let me come onto my terminal again, and we are on the jump box here. So if I SSH onto node 0, wow, they're impressed by that. And then I come in here, system kubelet. So here we have the kubelet binary and a configuration for it, kubeconfig again, because we want it to know where the cluster is. And then what do we have in here? Well, we just have some things like I mentioned, the container runtime endpoint. Here we're using Containerd, in my opinion, a good choice. We have some things here like cluster domain and a few things around authentication that, again, I won't get too much into right now. But yeah, so let's have a go at turning this on, and hopefully it works. Systemctl status kubelet. Cool, so it comes up properly, and you can't see the end of that line, but it says about it's watching for workloads to appear. So let's come back to the jump box now and have a look at our pod. And now our pod is running, which means this demo works, so that's great. You flatter me, you flatter me. Oh, go. Cool. Okay. Yeah?
So here, like, one second, you just...
Yeah, go for it.
So like we have started like the API server and we started the etcd, right? So here like so this will actually show you the etcd system file. So if you see the etcd system file, it says that it listens on the port 2379 here. Okay, so this is the port that the etcd is listening on. So when the API server should connect to etcd, it will be connecting, trying to connect to this port. So if you try to see now the API server file, if you now try to see the API server file here, Okay, so in the API server file here, you see something like this here. So this is how the API server actually connects internally to the etcd server, and that you see something here.
That's just my Mac being annoying. I hate this feature.
Yeah, if you see something here, you see something like all of the certificates. So this is how the authentication is taken care of using the public key infrastructure.
Yep.
So in the interest of time, we cannot explain authentication, but this uses the CS certificate, the client, and the CS root authority to authenticate. And lastly, if you run the command like the kubectl cluster info, you should be able to see that the cluster is up and running.
Yep, which we did earlier, and it's right there.
Yeah.
And we have running pods. OK, so there's one more thing left, and I just saw someone flash a 5-minute sign at me, so I should probably get onto it. So that's all well and good, but there's one thing missing here. We have not started something called kube-proxy. What the heck is kube-proxy? Well, when you are setting up a Kubernetes cluster, you're probably going to create services at some point. And services can be of many different types. I'm going to pick an easy type here of a node port. What does node port actually mean? It means that a port on all of your nodes for your cluster, a given port that is common across all of them, will expose a given service. Well, what's actually binding that port? Well, on each of the nodes on your cluster, next to the kubelet is running this thing called kube-proxy. And kube-proxy is binding itself to these ports, and it's forwarding traffic from them to the service that has been configured. In this case, we are not going to get as far as creating a node port, but we are going to start kube-proxy. And I'm sure someone is going to mention that kube-proxy doesn't necessarily bind to ports, it uses IP tables. Fair enough, but it's close enough in the same thing. So if I come through here and I have a look in my systemd, kubeproxy.service. So again, just like before, it has a config file, and in there we have a kubeconfig so that it knows where the heck the cluster is and how to connect to it. And then here we have a mode IP table, so it's going to use IP tables to do all of this binding. So if we just do a systemctl start kubeproxy and systemctl status kubeproxy, cool, so we have running kubeproxy. So after all that, we end up in basically with an architecture that looks something like this, without the jump box, because the jump box is not part of the cluster. It's just where I'm running commands, so I don't mess up my local computer. So to recap, we've set up now a running Kubernetes cluster in the most minimal sense of the word. We have our goal state and desired state being stored in etcd data store. We have controller manager that is causing our deployment to be turned into replica sets and then into pods. We have the kube scheduler and looking at our pods and scheduling it onto the node that we created. And we have the kubelet picking up that the pod has been scheduled and actually running it on the machine. And so we have a running Nginx server. And then after all that, we have the kube-proxy so that we could set up services in the future. So that was a very long way to run Nginx. So if you want to try this yourself, there's a QR code there to the repo by a certain person in the first row who's looking at this presentation. Again, if you do this in production, it's all your fault when it breaks. I'm not taking any responsibility for it. This is for learning and for some sick, twisted version of fun in some people's sense. That's all we've got. That's all we have time for. I think I saw the 2-minute warning just a second ago, so let's call it there. If you have any feedback, let us know. And yeah, and we'll take any questions. Thank you. Yeah. Is it?
Can you hear me?
Yeah, I can hear you.
Amazing, yeah. Thank you so much for that. That's really nice. You showed like how it works piece by piece. So, if, for an example, I was trying to set up like a home server using K3s. Which bits would K3s kind of be doing automatically for you?
Which components of K3s were you using? Were you using K3s up? Were you using K3s up, or were you just using K3s the base components?
Okay, so what I'm doing literally is setting up nodes using multipass and just some virtual machines, and just installing one of those nodes as a K3 master node. Yeah. Setting up some other 3 as worker nodes.
So kfreeze will be setting up the, API server in etcd for you. Although kfreeze is quite interesting because from memory, it uses MySQL instead of etcd, and it has an etcd binding to MySQL behind the scenes. I also am running a kfreeze server at home right now, which is taking up too much of my time. And then when you set up nodes that are actually running stuff, kfreeze is going to be responsible for actually packaging the kubelet and kube-proxy together. Kfreeze, the meaning of it is that there's not like a load of binaries, there's only 3 binaries. And so inside, it's basically just multiple of these components wrapped. If I go back here, so from here, maybe you could think of like kfreeze, the kube-proxy and kubelet are one thing, and then the API server, kube-controller manager, and kube-scheduler from memory are also one thing in kfreeze, and then etcd is actually just MySQL. Does that make sense?
Yeah, that's perfect. Thanks.
Awesome.
There's one more question I can ask.
Go for it.
Yeah.
You're the only one in the queue.
So in terms of the networking, you talked about kind of how you have the, sorry, what was it? You said kubelet as well as the kube-proxy, right?
Yep.
How does that relate to sort of the CNI? And like, I've seen conversations about Cilium, et cetera, like that. How does that relate?
So the CNI, the cluster network interface, is it's similar to the CRI in that it's a way that there is a contract that you can implement that allows you as an operator of a cluster to control how you actually set up your network routes and etc. within the spec that Kubernetes provides. So what does Cilium do? Cilium uses eBPF, and it uses that to create network routes across the cluster. It uses that to forward traffic, and it gives you a few extra things on top. There are other things. For example, Cilium leans into Envoy, and it may add like authentication layers and all sorts of non-trivial logic and etc. And then there's also the host machine that I think you can use our CNI tools and etc. So you can almost think of it like if the runtime you have containerd, Docker, Cryo, these offerings, and they all run containers, but they have slightly different feature sets in it and advantages. The CNI you can think of is the same thing but for networking.
Nice, perfect.
Cool.
Have we implemented the CNI within this, or?
Yeah, we did. What was it we used? I can't remember which one we used. I think we're out of time though, right? Sorry.
Sorry.
Come up.
Thank you. Great. Great. Thanks, everyone. That's the end of the Cloud Native Core curriculum for today. So we'll now be handing over to the teaching.